Polar form of complex numbers. Objectives: plot complex numbers in the complex plane, find the absolute value of a complex number, write complex numbers in polar form, convert a complex number from polar to rectangular form, find products of complex numbers in polar form, find quotients of complex numbers in polar form, find powers and roots of complex numbers in polar form. Plotting complex numbers in the complex plane. Plotting a complex number a plus bi is similar to plotting a real number, except that the horizontal axis represents the real part of the number a, and the vertical axis represents the imaginary part of the number bi. Plot the complex number in the complex plane. This is the real axis, and this is the imaginary axis. So we see the real part is 2, and the imaginary part is negative 3i. So we'll go right 2 on the real axis and down 3 on the imaginary axis. And that's our number, 2 minus 3i. For 1 plus 5i, we'll go to the right 1 on the real axis and up 5 on the imaginary axis, and we land here, 1 plus 5i. Finding the absolute value of a complex number. The first step towards working with a complex number in polar form is to find the absolute value. The absolute value of a complex number is the same as its magnitude, or absolute z. It measures the distance from the origin to a point in the plane. Given z equals x plus yi, a complex number, the absolute value of z is defined as the square root of x squared plus y squared. Here you can see demonstrated. If we would draw a right triangle in order to travel to our complex number, this dimension is 2 and this dimension is 4. So in the Pythagorean theorem, we have the square root of 2 squared plus 4 squared, which is the square root of 4 plus 16, the square root of 20, and simplifying down to 2 square roots of 5. So a complex number's absolute value is its distance from the origin. Find the absolute value. Here, z equals the square root of 5 minus I. So the absolute value of z is equal to the square root of square root of 5 squared plus a negative 1 squared, negative 1 being the coefficient of I. Now we simplify from here. This would be 5 plus 1. So we have the absolute value equaling square root of 6. For z equals 12 minus 5i, the absolute value of z will be the square root of 12 squared plus negative 5 squared. That's the square root of 144 plus 25, which is the square root of 169, which is 13. Writing complex numbers in polar form. Writing a complex number in polar form involves the following conversion formulas. X will be r cosine theta, y is equal to r sine of theta, and r is the square root of x squared plus y squared. If we look at the formula this way, the cosine of theta is x over r. If this is our angle theta here, then the cosine is adjacent over hypotenuse. The sine of theta is equal to y over r. Again, theta is here, and the sine of theta is opposite over hypotenuse. And r is the square root of x squared plus y squared. That's just from our Pythagorean theorem to be able to find the length of that hypotenuse, which is r, the radius of that circle. Making a direct substitution, we have z equals x plus y I. Z is equal to r cosine theta plus I times r sine of theta. And most of the time it will be written as z equals r times cosine theta plus I sine theta. R is the modulus and theta is the argument. We often use the abbreviation r cis theta to represent r times cosine theta plus I sine theta. Express this complex number using polar coordinates. For I, well, I know that this is 0 plus 4i, and my r is computed as the square root of 0 squared plus 4 squared, which is the square root of 16, which is 4. And I know that x is r times the cosine of theta, but r is 4. And I know that my x is 0. So really I have 0 equals the cosine of theta. This means that my theta is pi over 2. For y, I have y equals r sine theta. Now r was calculated at 4, and my y is also 4. So I really have sine of theta equals 1. And I know that the sine of theta is 1 when theta equals pi over 2. So in both cases there, I've seen that the theta is pi over 2. So now I can write my number in polar coordinates. Z is equal to r, which is 4, times the cosine of pi over 2 plus I sine of pi over 2. Or alternately, I can write 4 cis pi over 2. Negative 4 plus 4i. Let's first calculate r. r is the square root of negative 4 squared plus 4 squared. That's going to be the square root of 32, or 4 square roots of 2. Now I know that x equals r cosine theta. My r is 4 square roots of 2, and x is negative 4. So I'm looking to find where the cosine of theta is equal to negative 1 over square root 2, which is the same as cosine theta equaling a negative square root of 2 over 2 after rationalizing that denominator. And the cosine of theta will be negative square root of 2 over 2 when theta is 3 pi over 4. Knowing that my theta is 3 pi over 4, I can go ahead and write my number here. I have z equal to r, which is 4 square roots of 2, times the cosine of 3 pi over 4, plus I sine of 3 pi over 4. And again, this can be written as 4 square roots of 2 cis 3 pi over 4. Find the rectangular form of the complex number. Z equals 12 cosine pi over 6 plus I sine pi over 6. So I know that x is r cosine theta. My r is 12. My theta is pi over 6. So x will be 12 times the square root of 3 over 2, which is the cosine of pi over 6. So x is 6 square roots of 3. Now to find our y is r sine theta. So y is, my r is 12, my theta is pi over 6. Y will be 12 times 1/2. So y is 6. So putting this in rectangular form, x plus y I have 6 square roots of 3 plus 6 I. Now let's find the rectangular form of the complex number with r equal to 13 and tangent of theta equaling 5/12. So I know again that my x is r cosine theta. R is 13, but I don't know what my theta is. Now, tangent of theta is 5/12. So using some right triangle trig, if this is theta, then the opposite over adjacent is 5 over 12. Using Pythagorean theorem, this would be 13. So the cosine of theta is going to be 12/13. So I'll replace my cosine theta with 12/13. And this means that x is 12. Now for my y. Y is r sine theta. So y is my r of 13 times sine theta. Sine of theta is equal to the opposite over the adjacent. That's 5/13. So the sine of theta gets replaced with 5/13, and I see that y is 5. This means that my number is 12 plus 5i in rectangular form. Finding products of complex numbers in polar form. If z sub 1 equals r sub 1 times cosine of theta sub 1 plus I sine of theta sub 1, and z sub 2 equals r sub 2 times cosine of theta sub 2 plus I sine theta sub 2, then the product of these numbers is given as z sub 1 z sub 2 equals r sub 1 times r sub 2 times the cosine of theta sub 1 plus theta sub 2 plus I sine of theta sub 1 plus theta sub 2. This means z1, z2 can also be written as r1 times r2 times cis of theta sub 1 plus theta sub 2. Notice that the moduli are multiplied and the angles are added. Find the product of z sub 1, z sub 2, given z sub 1 and z sub 2 shown. So z sub 1 times z sub 2 will equal the moduli multiplied together and times the cosine of the angles added together plus I sine of, again, the angles being added together. So this is going to be equal to 8 times the cosine of 225 degrees plus I sine of 225 degrees. This is 8 times negative square root of 2 over 2 plus I times negative square root of 2 over 2, giving us negative 4 square root of 2 minus 4 square root of 2 I. Finding quotients of complex numbers in polar form. If we have z sub 1 and z sub 2 as shown, then the quotient of these numbers will be z sub 1 over z sub 2 equals r sub 1 over r sub 2 times the cosine of theta sub 1 minus theta sub 2 plus I sine of theta sub 1 minus theta sub 2. Z sub 2 cannot equal 0. The alternate way to write this is r sub 1 over r sub 2 cis theta sub 1 minus theta sub 2. Notice for quotients that the moduli are divided and the angles are subtracted. Find the quotient of z sub 1 equals 2 cosine of 213 degrees plus I sine 213 degrees, and z sub 2 equals 4 cosine 33 degrees plus I sine of 33 degrees. So z sub 1 over z sub 2 will be equal to 2 over 4 times the cosine of 213 degrees minus 33 degrees plus I sine of 213 degrees minus 33 degrees. This simplifies to 1/2 times the cosine of 180 degrees plus I sine of 180 degrees. This is 1/2 times negative 1 plus I times 0, so that gives us just a negative 1/2. Now finding powers and roots of complex numbers in polar form. Finding powers of complex numbers is greatly simplified using de Moivre's theorem. It states that for a positive integer n, z to the n is found by raising the modulus to the nth power and multiplying the argument by n. It's the standard method used in modern mathematics. Formally stated here, de Moivre's theorem, if z equals r times cosine theta plus I sine theta is a complex number, then z to the n equals r to the n times the cosine of n theta plus I sine n theta. Or z to the n is equal to r to the n cis n theta, where n is a positive integer. Here we simplify the powers of I. First, let's look at a pattern. I know that I is the square root of negative 1. I squared is negative 1. But what is I cubed? I cubed will be I times I squared. So it turns out that I cubed is negative I. I to the 4th could be viewed as I squared times I squared, which is negative 1 times negative 1, which is 1. Now, I to the 5th. I to the 5th could be written as I to the fourth times I. This is convenient because I to the fourth is just 1. So I to the fourth is 1 times I, which is I. I to the sixth is written as I to the fourth times I squared. Again, this is convenient because I to the fourth is just 1, and I squared here is -1, so I have -1. If you step back, you can see a pattern. The pattern is I, -1, -I, 1. I, -1. The next should be -I. Let's try. I to the seventh is I to the fourth times I cubed. I know I to the fourth is just 1 times I cubed, we saw above, is -I. So we get what we thought as -I. So let's try simplifying these powers. I to the eighth can be written as I to the fourth squared. Well, I to the fourth is 1, and 1 squared is 1. Another way to handle this would be to see how many times 4 can go into 8. It'll go in there evenly 2 times and 0 left over. So I to the eighth is equal to I to the 0, which is 1. Here I have I to the 31. Let's see how many times 4 can go into 31. If I have 7, 4 times 7 is 28, and remainder of 3. So I to the 31 is equal to I to the fourth to the seventh times I cubed. I know that I to the fourth is just 1, and 1 to the seventh is just 1, times my I cubed, and I cubed is -I. Evaluate the expression 1 plus I to the fifth using de Moivre's theorem. Recall that de Moivre's theorem says that z to the n is equal to r to the n times the cosine of n times theta plus I sine of n times theta. So for this formula, I will need to know r, the modulus, and I'll need to know the angle theta. R is going to be the square root of 1 squared plus 1 squared. So that's the square root of 2. What is theta? Well, I know if I would draw a right triangle, this is 1 and this is 1, given those components. So theta, I know that I have the tangent of theta is going to be the opposite over the adjacent. Tangent of theta is 1, and the tangent of theta is going to be 1 when theta is pi over 4. So I have both my r and my theta to put my formula together. I have z to the 5 is equal to the square root of 2 to the 5 times the cosine of 5 times pi over 4 plus I sine of 5 times pi over 4. This is 4 square roots of 2 times the cosine of 5 pi over 4 is negative square root of 2 over 2 plus I times the sine of 5 pi over 4 is also negative square root of 2 over 2. So z to the 5th then is going to be negative 4 minus 4i once we have that all multiplied out. The nth root theorem. To find the nth root of a complex number in polar form, z to the 1 over n is equal to r to the 1 over n times the cosine of theta over n plus 2k pi over n plus I sine of theta over n plus 2k pi over n, where k equals 0, 1, 2, 3, all the way up to n minus 1. We add 2k pi over n to that theta over n in order to obtain the periodic roots. Evaluate the cube roots of z equals 8 times cosine of 2 pi over 3 plus I sine of 2 pi over 3. Evaluate the cube roots of z equals 8 cosine 2 pi over 3 plus I sine 2 pi over 3. We have that z to the 1/3 is 8 to the 1/3 times cosine of 2 pi over 3 divided by 3 plus 2 pi over 3k plus I sine of 2 pi over 3 divided by 3 plus 2 pi over 3k. Simplifying this, we'll have 2 times the cosine of 2 pi over 9 plus 2 pi over 3k plus I sine of 2 pi over 9 plus 2 pi over 3k. So for k equals 0, we'll have z to the 1/3 equals 2 times the cosine of 2 pi over 9. If k is 0, this term goes away, so the angle doesn't change, plus I sine of 2 pi over 9 again. And for k equals 1, z to the 1/3 will equal 2 times the cosine of 2 pi over 9 plus, if k is 1, then we'll be looking at adding 2 pi over 3. So I'm adding 2 pi over 3 to my angle, and same here, plus I sine of 2 pi over 9 plus 2 pi over 3. Then we'll simplify. Z to the 1/3 equals 2 times the cosine of 8 pi over 9 plus I sine of 8 pi over 9. For k equals 2, we have z to the 1/3 equals 2 times cosine of 2 pi over 9 plus, with k equaling 2, this will be 2 times 2 pi over 3, or 4 pi over 3 that I'm adding, plus I sine of 2 pi over 9 plus 4 pi over 3. Then simplifying, I have
z to the 1/3 equals 2 times the cosine of 14 pi over 9 plus I sine of 14 pi over 9.